All right, Titans, welcome back. First off, do you know what the 8 said? No, dang it. Do you know what the 0 said to the 8? Nice belt. Think about it. Okay, so we have been solving quadratic equations for 2 weeks, and we are ready to move on to graphing quadratic equations. So today's lesson is actually going to be all about the vocabulary for quadratics, because there is a lot of vocabulary, and it's going to be a big part of understanding what we're doing is making sure you know the words that go along with it. A lot of it's actually familiar from IM1, hopefully, but we're going to recap that and go over all the key vocab for quadratics. So the first is parabola. Para what? Right? Some people, they try to call it a parabola, and then it just sounds kind of weird, but parabola. Basically, parabola is just the shape of the graph of a quadratic equation, right? When we graph a linear equation, we get a line. When we graph a quadratic equation, we get a U-shape, right? But the actual name of that U-shape is a parabola. So parabola is just the word for this U-shaped graph. It can be up, it can be down, but it's called a parabola. The next set of vocabulary words is knowing the difference between concave up and concave down. It's very simple. If the graph opens upward, then it is up. If the graph opens downward, meaning pointing down, then it means it is concave down. So I'll usually say opens up or opens down, but I know some teachers will be more specific and say concave up versus concave down. But if you're cave, if it's pointing up, you've got concave up. If you got down, concave down. Pretty simple. Absolute maximum and absolute minimum. I know we did this in IM1. An absolute maximum is the highest point on a graph. So this particular parabola, which is concave down, the highest point on this graph is right here, right? That is the maximum y value. It's the highest the graph goes. So because it is the highest, or the maximum that this graph reaches, this graph would have a maximum. This graph, on the other hand, when it changes direction at the bottom of the parabola, it creates a lowest point. So this point right here is lower than every other point on the graph. So this is called an absolute minimum. So if it has a highest point, it's a maximum. If it has a lowest point, it's a minimum. Anytime your parabola is concave down, the graph will always change direction at the top of the parabola, and therefore you will always have a max if the parabola is concave down. But if the parabola is concave up, that means it'll change direction at the bottom of the parabola, and you will always have a minimum. So again, concave down, opening downward, will always have a max, but concave up will always have a minimum. The vertex. All right, so the vertex is something that's new to quadratics compared to linear equations. The vertex is it's basically your min or max, right? It's the highest or lowest point. And so the vertex of this right here is just where the graph is changing direction from increasing to decreasing, or in this case, from decreasing to increasing. But it's the highest or lowest point, which is why we also say the vertex can be identified as either the absolute minimum or the absolute maximum. When we talk about the vertex, though, we always want to label it with an ordered pair. So this vertex right here, since the x-coordinate is 1 and the y-coordinate is 1, it has a vertex of 1, 1. Oh, let me try that again. 1, 1. So the vertex is at 1, 1. The vertex on this one is right here, which is a maximum, but it's at the ordered pair 2, 4. So we would say the vertex of this graph is at 2, 4. So the maximum is our vertex, which is 2, 4. This parabola, which is concave up, has a minimum, and this minimum point is also going to be our vertex, because it's in this case, the lowest point on the graph. And so the vertex of this parabola would be -2, -3. So again, the vertex is always your minimum or your maximum, and we list our vertex as an ordered pair. The next one is called the axis of symmetry, or sometimes we call it a line of symmetry. And you probably remember from previous classes that symmetry means it's symmetrical. So it's basically a mirror image or a reflection. So when we take, or I'll just read this here, a vertical line that divides the parabola into two congruent halves. So our axis of symmetry will be a line that goes up and down. It's always vertical with a quadratic and with a parabola. And it's because it divides it in half, it always, every single time, it'll always cross through the vertex of your parabola. So here's an example of an axis of symmetry. It cuts right through the vertex, splits it into a left half and a right half, right? It's gonna be the same on both sides. So for this one here, I can find my vertex, which is right here. And then my axis of symmetry will be a vertical line that goes straight through that vertex. And then naming the axis of symmetry, because it's a vertical line, all vertical lines are actually always x equals a number, because every x coordinate on this line will be the same. We could also think about it as this line only goes through the x-axis, so it's going to be an x equals. And the point that it goes through on the x-axis is 2. So the name of this axis of symmetry is x equals 2. I also made note of that up here, that the x-coordinate of your vertex, so the vertex here was 2, 1, the x-coordinate of your vertex is always the equation for your axis of symmetry. So since our vertex had an x of 2, the axis of symmetry was x equals 2. Likewise on this one, we're going to find our vertex, which is at -3, -9. And our axis of symmetry will be the line that goes straight through that. So I'm going to go like this. And the x value that we went through is -3. So our axis of symmetry is the line x equals -3. Or as I mentioned up here, the x coordinate of our vertex is always the equation for our axis of symmetry. So again, the x of our vertex is always the value for the axis of symmetry. And the axis of symmetry will always be x equals that number. Parabolas will have intercepts. We can have x-intercepts and y-intercepts. Y-intercepts are where a graph crosses the y-axis. We always write it out as the ordered pair 0, y. And quadratic equations will always have one y-intercept. It will always have a y-intercept. If we look at this graph here, we're crossing the y-axis at -3. And we know that it needs to be 0, y. So my y-intercept is 0, and then the y value of -3. For this graph, the y-intercept, where we cross the y-axis, is at 4. So that's going to be 0, 4. So again, every parabola will have one y-intercept, and the y-intercept will always be 0, and then the number. X-intercepts are a little bit different though. First off, it's an x-intercept, so it's where we cross the x-axis, right? So it's where we cross x, where we cross x. But what's a little bit different is you don't always have one. Because x-intercepts are really the same thing as the solutions to a quadratic. In the last 2 weeks, we've been solving quadratics, and we know that we could get no solution, right, if you had a square root of a negative. You could get one solution if you had square root of 0, and you could get two solutions if your square root was positive, or if you're able to factor it or complete the square, then you usually get two solutions. So because the x-intercepts are really just the solutions, right? So the solutions to quadratic equations are really the x-intercepts of the graph. It's possible to have 0 x-intercepts, 1 x-intercept, or 2 x-intercepts. It depends on the number of solutions. If the problem had 2 solutions, it'll have two x-intercepts. So this particular problem, we don't know what the problem was, but we do know that it would have two solutions because it has two x-intercepts. The x-intercepts are 1 and 3, and we'll always write the x-intercept as the x and then comma 0. So this one right here, the x is 1 and then comma 0. So 1 comma 0 is one of our intercepts. And then our second intercept is at 3. So our second intercept is 3 comma 0. So again, we know that this particular graph, if we were to solve the equation that goes with it, we would get two solutions because we're able to get two x-intercepts. Now, if the x-intercepts are the solutions, why doesn't this graph have any x-intercepts? Well, if there's no x-intercepts, that means the problem had no solutions. So when a problem had no solutions, it didn't mean we couldn't graph it anymore. It simply means that when we do graph it, the graph will not have any x-intercepts. So it is possible for your x-intercepts to have none of them. It just means, again, that the problem had no solutions. Our other option will be to have one x-intercept, and we'll look at an example of that in a few minutes. All right, domain and range. This one always trips people up. I don't know why. I think it's really simple. Domain is simply all of your x values that are included in a function, and range is all of your y values in a function. So domain is x, range is y. You can think about that alphabetically. D comes before R, X comes before Y. So the two that come first, domain and X, and then the two that come second, range and Y, they go together. If we look at a parabola and we're looking at the domain, we're looking at all of the possible X values, the graph actually goes left forever, and it keeps going out to the right forever. Even though it's going down, it's still going out to the left and out to the right. Same thing on this one, it's going up, but it's still creeping to the left, it's still creeping to the right. So your domain is always, every single time for a quadratic function, is going to be all real numbers. If I go to an x value of 6, that will be on the graph. I have to go down a long ways, but eventually I get to a point where I hit the graph. So this will appear on the graph. There will be an ordered pair on the graph that'll be 6 comma something. Every x value will show up. Same thing on this, goes left forever, goes right forever. Domain, all real numbers. So every quadratic equation, or every graph of a quadratic function, the domain will be all real numbers. The range, however, will not be all real numbers, because if we think about it, if the range is all of the y values, this graph here goes up, 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 but it stops going up once you get to the vertex, and then it goes down again. So the highest y value that this graph reached was 1. So there will never be a point on this graph that has a y value above 1. So every point on this graph will have a y value that is 1 or below. So we write that as the range being y is less than or equal to 1. Every point. If I go right here, this is the point 4, -3. That y value is less than or equal to 1. No matter where I go, it's going to be a number that is 1 or below. On this graph, however, we do have numbers that go up, right? We can go all the way to infinity. The lowest this graph goes is right here, which is a y value of -2. So we know that every point on this graph is going to be above a y value of -2. So the range, our y values, is going to be everything greater than or equal to -2. So essentially, when we're doing range, it'll always be y is greater than the y of the vertex. In this case, it was greater than, right, this y value of the vertex. Or it'll be less than or equal to the y of the vertex. If it's opening down, we're going to be less than or equal to the y of the vertex. All right, the last set of vocabulary, and then we're going to do a few examples, is looking at intervals of increase and decrease. every parabola will go up and down. So this particular parabola goes down and then it goes up, right? We look from left to right. If it was upside down, then it would go up and then down. But we do know that every parabola increases and decreases. So the interval of increase is going to be every x value, and this is the important part. This is where students mess up. We're only going to look at the x values, but it's the x values where the graph is increasing. So if I highlight where this graph is increasing, I notice that right here is where it's not doing either, but the rest of the graph is going up. So it is increasing. But a lot of people want to look at the y values now and go, oh, -3, and no, that's the range, right? The range is the up and down. The interval of increase is the x values at which the graph is going up. So if I draw my line of symmetry, right? Everywhere to the right of my line of symmetry, the graph is going up. It is increasing. At -1, if I go to the graph, it is increasing. If I go to 0 and I go to the graph, it is increasing. If I go to an x value of 1, the graph is increasing. So no matter where I'm at, to the right of -2, this graph is going up. So the interval of increase is from -2 to infinity. The x value of -2 is where it starts to go up. And then as we look at every other x value, the graph still goes up. The interval of decrease, however, is where the graph is going down. And so the graph is decreasing for the entire graph, from all the way from -infinity until it gets to here, right? Until it gets to the axis of symmetry. So until it gets to -2, the graph is going down. So the interval of decrease is from the beginning of the graph, which is an x value of -infinity, until we reach the axis of symmetry, or the vertex, which is at -2. So again, the graph goes up from -2 and beyond, but it goes down from -infinity until -2. All right, we're going to go through 4 examples. I'll try to pick up the pace a little bit. I know I'm kind of dragging here. Function family. We are dealing with the function family of quadratic. Right? How do we know it's quadratic? Well, 1, the equation has x squared as its largest exponent, and 2, it's a parabola. So speaking of parabola, the shape of this function, or the shape of the graph, is called a parabola. Is it concave up or concave down? Well, it's opening up, so that is concave up. Because this point here is the lowest point on the graph, we have a minimum. X-intercepts, this one, we only actually touch the x-axis one place. So this one only has one x-intercept, and it's at 0, 0. It's a little bit unique because the y-intercept is also at 0, 0. So it is possible for an x-intercept and a y-intercept to be at the same place. The vertex is also 0, 0, right? That's where we're changing direction. The axis of symmetry, if we go straight through the middle of the vertex, that's going through 0, so x equals 0. Domain, this graph goes forever to the left, it goes forever to the right, so domain is always all real numbers for a quadratic function. The range, however, we're looking at the y values. The lowest that this graph goes is right here at 0. It never goes below 0. So every y value on this graph is going to be greater than or equal to 0. Interval of increase is where our graph is going up. So if I find where the graph is increases, it increases from here forever, right? But it's important that I don't look to see how high it's going. I'm looking at the x values. So the x value right here is 0. And then as we go this way, the graph continues to go up. So my interval of increase is from 0 until forever. 0 until infinity. But the interval of decrease, this graph decreases all the way until it reaches this point, which is 0. So everything left of 0, no matter where we are on the graph, it will be going down. So the interval of decrease will be negative infinity to 0. Okay, example number 2, it's basically the same graph, just flipped upside down. So that's going to change a few things about it. It's still a quadratic. We still call it a parabola. But this time, because it's opening down, it's going to be concave down. Because it opens down, we have a high point, which is called the max. The x-intercept, once again, we only have one x-intercept, and it's at 0, 0. The y-intercept is also at 0, 0. And the vertex is also at 0, 0. The axis of symmetry, if we go straight through the middle, that's an x value of 0 as well. Domain, it goes left and right forever. So domain for quadratic, all real numbers. But this time the range is not going to be greater than, it's going to be less than. Because every point on this curve, the y value is below 0, right? Or right at 0. So the range for this is going to be y is less than or equal to 0. The graph is increasing this time on the left side, so it goes up all the way until we get to the axis of symmetry. So it's increasing from the beginning of the graph, negative infinity, right, as we look this way, all the way until it gets to 0. That's where it's going up. And then once it hits 0, now the graph is going to go down forever. And a lot of people try to put negative infinity right here because it's going down. But remember, we're looking at the x values. So as the graph goes towards positive infinity, the graph is decreasing. So the interval of decrease is from 0 until an x value of infinity. It'll decrease forever. All right, 2 more examples. These ones don't have a vertex at 0, 0, so we'll have a little bit different information now. First off, function family, still quadratic. Shape, we call it a parabola. Concave up or concave down, well, it's definitely opening up, which means it has a minimum. This time we do have x-intercepts. We have 2 of them. We have them at negative 7, 0 and negative 1, 0. So that means this problem would have 2 solutions if we solve it. Meant to put that right there. The y-intercept, this time our y-intercept is up here at 7. So the y-intercept is 0, 7. The vertex is where we change direction. So again, way down there, which is negative 4, negative 9. We know that the axis of symmetry always goes through the vertex. So the x of our vertex will also be our axis of symmetry. Goes through negative 4, right? It goes through the negative 4, which will cut through the vertex. Our domain, still all real numbers, because the graph goes forever left and right. But our range, the lowest our graph goes is right here, which is a y value of negative 9. So every y value on this graph is going to be negative 9 or above. So we could say that the y values will all be greater than or equal to negative 9. Interval of increase from the axis of symmetry and to the right, that is where the graph is going up. So it's increasing from negative 4 until infinity, which means it decreased everything from negative infinity until negative 4, and then it started to go up. So it's decreasing from negative infinity to negative 4. And finally, we'll do one more example. Function family for this one, still quadratic. Shape, still a parabola. This time it's opening down, so that's concave down. It has a maximum because we have a high point. X-intercepts, this time we don't have any, which means if we solve this, there will be no real solutions. So no x-intercepts. Our y-intercept is right there at negative 3, so 0, negative 3. Our vertex is that max, which is at 1, negative 2. We know the axis of symmetry always goes through the vertex, so it'll have the same x value, x equals 1. Domain, all real numbers. Range, this time every number or every point on the graph is going to be at -2 or below. So all of your y values are less than or equal to -2. The graph increases until it gets to the axis of symmetry. So it's increasing all the way until it gets to right here, which is the axis of symmetry of 1. So it's increasing from -infinity until it gets to that x value of 1. But once it hits 1, the graph goes down forever. So as we go to the right, the graph is decreasing. As we're going towards an x of infinity, the graph is going down. So the interval decrease 1 to infinity. All right, I know that's a lot of information, but wanted to get all that vocabulary out there to you up front. We're going to be using these vocabulary words for the next 2 weeks for sure, actually beyond that, but we're going to be using them a lot in the lessons the next 2 weeks. So hopefully that made sense. If you need help, rewind, watch again, Google, YouTube, Zoom with your teacher, email, all that good stuff. Hope you guys are doing well. Talk to you later.